are going live. Okay, we should, in theory, be live. Hey, everyone. Welcome to a very special time of open space. It's morning for me, but it is afternoon, evening in Europe, and that's important because my guest, Dr. Pekka Janhunen, is living in Finland. Dr. Janhunen, welcome to Open Space.
Thank you.
So you might not know, but you are a bit of a celebrity around these parts here on my channel. I have covered your research work. I did a whole video. I think I made a mistake. I got ions backwards. I don't know if you saw it, but we covered your idea of electric sails, and we have brought this up a couple of times in other episodes. So I know that my audience, some of my audience, is actually very familiar of the work that you have been doing. But for those who don't know, who are you and what do you do?
Yes, so my name is Pekka Janhunen, and I'm the inventor of the Coulomb drag propulsion, which includes the electric solar wind sail and the so-called plasma brake for satellite deorbiting. My background is space plasma physics, so I'm not an engineer, but I'm a scientist as my background.
And
I'm working at the Finnish Meteorological Institute as a researcher.
Right. So your background is in plasma physics and sort of the plasma from the sun, the solar environment, and so where did this idea of the electric sail, where did this come from?
It came from an ESA project. So ESA is the European Space Agency. So ESA, I mean, that was back in 2002 or something like that. So ESA was interested in the so-called magnetic sail idea that had been proposed earlier, and they wanted a scientific study of that idea. And we were selected to study it, and then we studied it, and then made some kind of theoretical study and said that yes, it would work in theory, but you need the superconducting cables and so on, and so it's technically difficult to build.
And so just to understand this distinction, yeah. So what is the idea then of the magnetic sail? Let's start there first.
Yes, okay. So the magnetic sail is basically artificial magnetosphere. So it's like a magnetic bubble which is pushed by the solar wind. Just in the same way as the solar wind is pushing Earth's magnetosphere. So it's also sailing with the solar wind.
Right. And so,
whereas the electric sail that we are talking about here is a little bit similar thing, but we use the electrostatic field instead of the magnetic field for deflecting the solar wind flow.
And so just to sort of more deeply understand, right? We've got the solar wind that is coming from the sun, and it is containing ions, it's containing electrons, it's containing protons, and they are charged from the sun's magnetic field. And so the solar wind is pushing out from the sun, and these kind of clouds of material have an electric charge and a certain level of like a magnetic field as they are moving through the solar system, right? And you're looking to interact with that.
Yes, that's correct. But the magnetic field of the solar wind is not important for this application. So it's a passive quantity which is carried along by the solar wind.
Right. Yeah. And so the idea of the magnetic sail is that you're essentially trying to be pushed by you're trying to, I guess, the way magnets repel each other, right? That you're trying to.
No. Also, the magnetic sail is pushed by the dynamic pressure of the solar wind flow.
Okay.
So the only difference is that in the magnetic sail you create a magnetic field obstacle for the solar wind flow, whereas in the electric sail you create an electric field obstacle for the solar wind flow.
And creating a large magnetic field is a very energy intensive process. We've covered this idea quite a bit in the past, where people have said, could you surround astronauts with a magnetic field to protect them from space radiation? And every attempt to figure this out so far, the answer has been no. You need it's too expensive. It's too complicated. It makes more sense to just surround people with lead.
Yes, in case of astronauts, there is also another kind of more fundamental problem with the magnetic field, and it's that humans cannot tolerate extremely high magnetic fields. So, and then the topology of the magnetic field should be such that the manned compartment is, I mean, that the field cannot exist, must not exist in the manned, in the volume where people are. But then that creates a problem that the secondary cosmic radiation, which is produced from the walls of the structure, it gets trapped into this field-free region, which is the same region where the people are, and then the secondary cosmic ray particles are moving back and forth there, and they are dissipating then their energy eventually in the flesh of the people, basically, and in the walls. So,
right. So you're sort of trapped in there with the radiation that you're trying to protect yourself from.
Yes, or the secondary particles of, so you have some primary particles which are able to penetrate the primary shield, but then the lower energy secondary particles created by those, they are trapped.
Right. So you're sort of cooked in your own
And I
oven.
think this is not too widely known. So it was pointed out by Eugene Parker in about 15 years ago in one of his publications, but I don't think it's extremely widely appreciated, this kind of fundamental problem.
That's really interesting. You're the first. You're exactly right. I mean, we've covered this idea quite a lot, and I've never heard this before. That essentially the process of blocking the most dangerous radiation essentially then traps the secondary particles inside the field that you're trying to protect with more particles. And like, do you need to make another field that protects against those particles? Like, it's,
Yes, but you can't do that because humans cannot tolerate that high fields.
Yeah, that's interesting.
So because I mean, humans might tolerate it if they are completely stationary, but as soon as they start to move across the field, then there is an induced electric field across the human being, and there have been experiments that you get a salty. Even in a rather moderate magnetic field, you get a salty taste in your mouth if you move in that field, because there is some electrolytic process in the saline of your mouth.
Oh, that's really interesting. Oh, that is so great. Thank you so much. I had no idea. That was like just a gigantic blind spot in my knowledge, and that's wonderful.
Yes, right. I learned this quite recently by reading, by randomly finding this publication by Eugene Parker from 2005.
Oh, that's interesting. Okay, so let's go back. So you were studying the idea of the magnetic sail, and it didn't look like it was going to be that effective, but then you considered the idea of an electric sail instead.
Yes, just because I'm a physicist by education, so in physics the electric and magnetic fields are kind of two sides of the same coin, so to say.
Yeah.
So it's natural to ask that if the magnetic field doesn't work so well for this purpose, for tapping into the free momentum flux of the existing solar wind, then maybe the electric field does the same trick. So
then practically then, what would an electric sail? How does it function?
Yes, it consists of very long and thin metallic tethers which are kept biased at a high positive potential with respect to the solar wind plasma. So, for example, 20 kilovolt potential with respect to the plasma, and then the tether creates around itself an electric field which is pointing away from the tether, and this electric field deflects the solar wind protons, and therefore it taps momentum from the flow of the solar wind protons. It also changes the trajectories of the solar wind electrons, but that doesn't create much force because the electrons are so lightweight particles that almost all of the momentum density is in the ions, which is mainly in protons in the case of solar wind.
And so the key is that you are getting the momentum change from from deflecting the protons that are part of the solar wind that are coming from the sun.
Yes, exactly.
Yeah,
That's
okay.
a good summary. Yes.
And so then how does this force that's coming from the sun that you're able to tap into, how does it change as you move farther and farther away from the sun? Where is it most effective and where does it sort of start to tap out?
Yeah, that's a great question. So the answer is that it decays as 1 divided by the distance from the sun. So 1 over r, where r is the distance from the sun. So the dynamic pressure of the solar wind, so that means how many newtons per square meter dynamic pressure, that decays as 1 over r squared, 1 over distance squared. But the plasma physics of this penetration of the electric field into the surrounding plasma works in such a way that this electric sheath, as we call it, sheath region, which is around the tether, it also gets wider when the plasma density goes down, and that partly compensates for the decay of the dynamic pressure. So as a net result, then it goes such that
but
it's 1 over distance.
Right, but 1 over distance is dramatically better than what you would get with the illumination. Like when you're running a solar sail, you're looking at 1 over r squared, right?
Yes, that's exactly true. Yes. So if we go to Jupiter distance, for example, then we are 5 times more effective compared to the solar sail than we were at 1 AU distance. And by the way, this does not only hold for the solar photonic sail, but it also holds for the common, the already nowadays used ion engines, electric propulsion, solar electric propulsion. Because the solar electric propulsion uses electric power, which comes from the solar panels, and the illumination of the solar panels goes down also 1 over r squared.
Right. So then where do you see this being a practical, like, as you said, we already have solar electric propulsion, we have ion engines, we have chemical propulsion. People are starting to consider perhaps light sails. Where do you see the electric sail outperforming and being the most useful propulsion system for exploring the solar system?
The applicability is in principle quite wide. So it could replace I would say that it could replace most of the low thrust propulsion applications, which means solar electric propulsion and photonic sails. There are some limitations. So one limitation is that the electric sail does not work inside Earth's magnetosphere because there is no solar wind in the magnetosphere. So we can't use it for lifting satellite orbits, and that's of course the major commercial application. So taking satellites from low Earth orbit to geostationary orbit, for example. So we can't do that.
Where could you start if you were in orbit around the Earth?
Well, roughly speaking, halfway the moon distance.
Okay.
But it depends on because the magnetosphere is not a sphere actually, but it has a long tail in the night side. But roughly speaking, halfway moon distance.
So not even like geostationary orbit, you couldn't use them.
No, it's still inside the magnetosphere. Right. So the geostationary orbit is about 6.6 Earth radii from the center of the Earth, and the magnetopause on the day side is about 10 Earth radii.
Right. So say the lunar gateway could have an electric sail on board to maintain its orbit.
Yes, in principle, yes, they could have, yes.
Yeah, okay.
And then the other restriction is that the maneuverability of the electric sail is not perfect because it's a large system, so it takes, we can vector the thrust by tilting the sail with respect to the solar wind, but it takes some time to tilt the sail because we do the tilting by the electric sail effect itself. So if we decide to tilt the sail to do this kind of maneuver, then it takes a couple of days typically with typical parameters. And during those couple of days, of course, it all the time produces propulsion in some direction.
Right. I'm kind of imagining you've got this central hub, and then you've got these many, sometimes kilometer-long tethers, and you're
Yes.
trying to turn the whole thing as a unit into a
Yes.
new tack. But
Yes.
but I know, like, one misconception that a lot of people have with solar sails is that they can't be used, that they can only go away from the sun. But that's not true, right? Solar
Yeah,
sails,
no, that's not true.
you're
No.
in orbit, and so if you turn one way, then you raise your orbit, and then you're able to move outward from the solar system. You turn the other way, and you're starting to lower your orbit. You're using essentially the light pressure as a brake to bring you closer and closer to the sun. So in theory, could you use, say, an electric sail to go
Yes,
down to
absolutely.
the sun, to like visit Mercury?
Yes, absolutely.
Yeah.
So in the same way as in the solar photonic cell, we can do the same in the electric cell.
Yeah, yeah. So I would love to talk about just some kinds of missions that, we talked about sort of where it performs. So essentially not at Earth, not at Jupiter, everywhere else is fine. What are some ideas of some missions that you're very excited about, that you think would work really well with an electric sail?
Yeah, so there is nowadays a startup company in Finland whose name is Aurora Propulsion Technologies. And they are kind of trying to looking into commercialization of the electric sail and also the plasma brake for deorbiting satellites, plus some other more conventional stuff, that means cold gas thrusters. Anyway, this company, together with me, we have developed a mission concept called North Star. It's a concept that we could fly out from the solar system a very small payload, maybe 1 kilogram payload, at high speed, using the electric sail, and maybe towards the North Star, because we can, with the electric sail, we are not restricted to only flying in the ecliptic plane, so we can also fly perpendicular to the ecliptic plane if we want to.
That's really interesting. So you just slowly change your trajectory and then just fly perpendicular to the solar plane.
So we can do that if the payload is enough small and if we have enough of these tethers. And of course, in this kind of mission, there is a challenge how to get, not only for the electric sail, but for the payload, how to get power, how to get electric power in order to transmit some data to Earth, and then how to have this antenna which transmits the data. So we have come up with some kind of innovative concept how to do that. So we would use an inflatable, maybe 2.5 meter diameter reflector antenna, which doubles as a solar collector. So we get power from the sun, and we get we get a radio antenna by the same hardware, very lightweight hardware, and this enables us to do this mission without nuclear energy whatsoever.
Okay.
That kind of makes it affordable. So it's fully solar powered, fully environmentally benign.
Right.
But still, we could transmit data from about 30 AU distance back to Earth. And the scientific mission would be to, for example, to measure the background light of the universe with a telescope. So, because this is a measurement that has to be done outside the zodiacal cloud, because the zodiacal cloud is the dust cloud which comes from the asteroids originally, which surrounds the Earth. So if you try to measure the background light level of the universe from Earth orbit, you can't do it very much because this zodiacal light is disturbing you.
Right.
But if you fly outside this zodiacal cloud, then you can make this measurement.
Right, and so all astronomy right now is hampered by this zodiacal light, that is this dust that is left over from the formation of the solar system. It is always in every picture that astronomers take. And
yes,
so
that's absolutely right. And of course, for most astronomical measurements, it doesn't matter. But if you try to measure really the background optical light from the distant galaxies, the average background light of the universe especially, for example, on the optical wavelength or some other wavelength, then you enter into this problem.
That's interesting. And so
run into this problem.
Right. And so you figure that you could have a a probe, like it would work practically out to a distance of about 30 astronomical units, that you could still, using a parabolic dish, you could both concentrate the light from the sun to provide energy, but also be able to use that as a transmitter to be able to send data back to Earth. And you could be out in the 30 astronomical unit range, which is like Pluto.
Yes, that's Pluto. Yes, so roughly there we could still have enough power for
Right.
running the transmitter. After that, we basically run out of power, and also this radio communication starts to become infeasible.
And you saying that's just solar power, that's not with using a nuclear battery. But if you did put a nuclear battery, like what is on the Voyagers or on New Horizons or something like that, then you could go where if power wasn't a problem, with a nuclear battery, how far could you go? Could you go out to hundreds of AU? Could you go?
Yes, sure. Yes, but of course it would take time. So,
of course.
But I mean, the speed would be something like 50 kilometers per second, the final speed here. So what we are trying to reach.
Yeah.
So,
that
means
one
AU
sweet spot is 1,000 AU. If you can get to 1,000 AU, then you can use the sun as a telescope.
Yes, yes. I think it's 550 actually, but yes, somewhere there.
Yeah. And so, in theory, this spacecraft, this propulsion system, could take you out to those kinds of distances faster than almost any other method.
That is true. Yes. So then the question is mainly the data. I mean, if you have some kind of nuclear source on board, then the question is that. Then the question is main question is the communication link, and of course, what is the weight of the nuclear power source? That's quite important parameter in that kind of mission. We haven't looked into that because we have thus far only analyzed this solar powered case, because these nuclear things are very, very expensive in practice. So the idea is that this mission we could implement with less than 10 million budget or something like that.
That's amazing. And one of the other missions, and we reported on this, I think it was about 2 years ago, that you were proposing that you could make scaled down versions of these that could, say, visit a whole bunch of asteroids, like each individual probe. So how small can this come down to be and still be practical?
Yeah, that's a good question. So I mean, people have analyzed that concept further, and it's about 3-unit CubeSat currently, what can be flown. So it's only one tether, one electric cell tether, 20 kilometers long, and then one 3-unit CubeSat weighing about 4 to 5 kilograms.
Right.
And then the instrument is a telescope whose aperture is perhaps 6 centimeters or something like that. For looking, and then one makes asteroid flybys, and then one important thing in that kind of mission architecture is that you need autonomous optical navigation. So because in that case we wouldn't be able to maintain radio contact with the Earth all the time. So the probe has to be able to fly on its own until it then at the end it makes an Earth flyby.
I love this idea.
Where it actually downloads all the data, downlinks all the data it has gathered down to Earth at low cost. But it requires we require software or navigation which works autonomously during the trip. In principle, this was done already 20 years ago by Deep Space One.
Yeah, that's right. Yeah. But I love this idea that you would just launch 10, 50, 100 of these little CubeSats.
Yes.
Each one would deploy its single tether for being able for propulsion. And then they would all just go out into the asteroid belt or just out, into the Trojans or everywhere across the solar system and just take all their pictures, take all the data that they can, and they follow this big long orbit, and then they come back to the Earth and they dump their data, and then they get their new orders. Now you're going here and here and here, and then they maneuver themselves autonomously, and you could just imagine that once you had enough of these going, every every 5 years, after it would be ongoing, just be like new probes are coming back every couple of days with more data, more analysis of a new asteroid. It would be game changing. And I know most
Yeah.
asteroid researchers would, they've only seen up close, you know, 5 asteroids that they've got good
Yes.
data, and so that's not enough of a sample for the solar system. You want
Yes.
hundreds, you want thousands, and that's how you would do it.
Yes. Yes. That's how you do it.
Yeah,
So if you want to view a large number of asteroids from close distance, the only way is to have lots of spacecraft, obviously.
yeah,
And the only way to make it affordable is that the spacecraft is very small.
yeah.
So there is kind of no way out of this fact,
So,
basically. So
so let's talk about flight time. So let's say you did want to send a probe out to, say, Pluto. How long are you looking at for it to be able to make these kinds of distances?
uh, I don't remember.
To the nearest
It might be
decade.
less. It's about 10 years or maybe 8 years. But of course, it all depends on the payload. So it's a
Right.
trade-off between the payload and the time always.
Yeah.
And of course, now we have to remember that if we go to Pluto, then we can't come back. So then it's only flyby.
Yeah.
So unlike asteroids, so from the asteroid main belt, we can still come back in, and the and this trajectory. I mean, this trip takes about 3 years in that case.
Right. You
Even from you mentioned Trojans. So Trojans we could also, in principle, cover with the same mission architecture. It's a little bit more challenging because
right.
there is so much less sunlight at Trojan distance. I mean, Trojans are 5.5 astronomical units.
Yeah.
So the trip would take longer. So it would be more challenging from the engineering point of view. But yes, it would be quite doable as an extension of this multi-asteroid touring concept that we already have.
Now I know that you have already launched a prototype a couple of years ago. How did that
Yes.
work out for you?
Well, we encountered some technical problem, which was so basically the reel where the tether was stored, it didn't rotate, and we know now the reason. So the problem was basically in the motor. So it was not in the tether or the deployment of the tether itself, but
Right.
it was kind of just in the plain old mechanics of the reel. So that was a CubeSat mission. So it was a shoestring budget and so on.
Yeah.
Only 1 kilogram satellite.
And it was going to be in
And
low Earth orbit anyway, so it wouldn't
low Earth orbit anyway,
so it
yes.
wouldn't have
And
worked.
one restriction. So we had to select a rather low torque electric motor because we wanted to select an electric motor which has no magnetic fields inside, because so we selected the Piezo electric motor for that reason, and the Piezo motor had rather low torque,
Yeah.
and that meant that any kind of mechanical glitch was kind of it was kind of sensitive to. There was not so much margin between the
Right.
torque that it could produce versus the friction that it had to overcome. And the reason was that if I mean, the satellite was so small that if there would be any stray magnetic fields in the motor, then that would have disturbed the attitude control system of the satellite, because the satellite flies in Earth's magnetic field.
Yeah, yeah.
So that's kind of all things that if you have small budget, then you have to make certain compromises,
Right.
and then at the end it increases the risk level in some way or another.
So it didn't work, but
It didn't work in that sense.
But are you working on the next prototype version?
Yes, we are now building actually a new experiment, which will fly almost identically. We will actually building 2 experiments. One is to fly in a Finnish CubeSat called Fraser Cain. The other one is flying in Estonian CubeSat S-Cube 2. And these experiments will be almost identical.
Yeah.
But the launch schedules of these satellites are kind of proceeding independently from each other. But they are both almost at the same in the same phase now. So we should deliver our hardware next autumn. I mean, in the coming autumn.
Right.
So we are kind of busily making Tether, and we have almost built this reel and motor and electronics now. So
So
we are working with that.
so there's another technology that you're working on as well that you call the plasma brake.
Yes, so the plasma brake is a variant of this electric sail. So the hardware is pretty similar. Uh, the plasma physics is also kind of reminiscent, but it's different because we use different polarity of the voltage. And the purpose of the plasma brake is to deorbit satellites, so that is to remove orbital debris.
Right, right. And so how would the two work together?
Uh, I mean, the hardware
It's the same thing
is
essentially.
similar, not quite, not almost the same, but very similar to each other. So the reel is similar. The tether is it can be similar, but it can little bit optimized differently.
Yeah.
Uh, and then the high voltage part is different. So in the electric cell, we need about 10 or 20 kilovolts of positive voltage to the tether, and we need an electron gun for pumping out this
Right.
negative charging from the system. But in the plasma brake, we need only 1 kilovolt negative voltage source, which keeps the tether at minus 1 kilovolt with respect to the spacecraft
Right.
and the plasma.
And so when would you use the plasma brake?
That's the end of life operation after the satellite mission is complete.
Oh,
so we
okay, okay,
activate
okay. So you would have a satellite that was orbiting the Earth. It was time for it to die, and it
Yeah.
would extend its plasma brake, and then
Yes.
it would wind itself into the atmosphere and burn up.
Yes, exactly,
Right,
exactly.
right.
And the point is that it can do this with low mass and low power.
Yeah, yeah. And I know
So
that
we
there are some other groups like Tethers Unlimited. They developed a descent, a tether, a similar system, but I don't think it
Yes.
had any electrical function. It was just just added the
Yeah, that's an
drag. Yeah,
aerodynamic drag tether. Yes,
yeah,
but our system has the benefit that the tether is very thin and very so it makes the system very lightweight. I would think that it's about one order of magnitude more lightweight than these.
And does it also work in a higher altitude? Because
Yes, I mean compared to yes. So actually, so there are now two comparison points. So one is this this aerodynamic tether that you were mentioning. The other is the so-called electrodynamic tether, which is yet another variant of the tether. So that uses the magnetic force.
yeah,
So it also deploys a tether, but much thicker than our tether.
right,
And the benefit of our system is that our tether is so thin. It is so thin that it's not threaten. It's not a threat to other satellites. So even if our tether collides with a live spacecraft,
right,
it won't. It makes a so small scratch that
right.
it's insignificant because similar scratches are produced all the time by the natural micrometeoroids on
Yeah,
all satellites. But if these electrodynamic tethers and these aerodynamic tethers, I think they are much thicker than
right.
ours. So if that kind of tether hits
Yeah.
another spacecraft, then it's a more severe consequence.
So in theory, could you even deorbit a geostationary satellite?
No, because no. So our there is not enough plasma in the geostationary orbit. So we could deorbit from up to, let's say, 1,200 kilometers or something like that, or
Right.
1,500, perhaps 1,500 kilometers. So we could still deorbit these mega constellations. So that
Yeah.
have been designed for low Earth orbit, but we can't deorbit navigation satellites or geostationary satellites, unfortunately.
Right. 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 All right. So now I want to go into just the far, far future,
Yes.
and that is like, is there any application for trying to go to another star system?
I would say not really, because the
Oh.
theoretical maximum speed of the electric sail is the solar wind speed, which is in the so-called fast solar wind is 800 kilometers per second on average. And that's kind of, with that kind of speed, the trip to Alpha Centauri would take still, I guess, more than, several thousands, 2,000 years or something like that.
Right. So
Yes.
that's fast, but it's not fast enough.
it's fast in the solar system times in the solar
Right.
system scale.
Yeah.
It's fast enough for almost any application in the solar system, but it's not fast enough for interstellar
Right.
trips.
What about as a braking system? So if you did send your spacecraft to another spacecraft using, say, a laser sail, and then you
Yeah.
deployed an electric sail once you wanted to slow yourself down, would that work at
Yes,
all?
that might work in principle. The issues there are, of course, the durability of the tethers in that and that kind of very fast
Right. You're going 10% the
stream
speed
of
of
plasma
light.
and dust that comes towards the spacecraft. But yes, it's kind of it has been looked into.
Yeah.
I haven't analyzed the numbers myself, but it has been looked into, and at least it's a theoretical possibility. Yes.
Interesting. Okay. All right. Because that's half the problem, right? Half the problem is getting up to a very fast
Yes.
flight time speed. The other half of the problem is slowing yourself back down again once you get on the other side. So I would love to ask, I've got some questions now from the audience that I want to pass along. This one comes from Arjone. I don't know if this is so. Could the sail be used for data transmission, or would the sails actually hinder it?
Uh, Neither. So this is actually this question is commonly asked, and well, my answer is that you can't really. I mean, the main reason is that the resistance of, I mean, the tether wires are so thin that the electrical resistance per length unit per meter is larger than the so-called free space resistance. So it means that if you try to use it as a transmitting antenna, you lose most of the power into heating the tether wires.
So there's no way that you could use the way it's interacting with the solar wind as a way to communicate. I mean, with really powerful radio telescopes, it's amazing what you could have a cell phone on the moon and someone could detect you making your phone call from Earth using some of the big radio antenna that we have here on Earth. And so you would anticipate there's some kind of way that the sail is interacting with the solar wind with the electricity, and that may create some kind of radio
Yes,
signal that is.
yes, it might create some radio signal, but the bandwidth is, I mean, the radio frequencies would be rather low in that case, and that
Right.
means that the data transmission bandwidth would be relatively low.
Yeah.
And also the antenna on ground would have to be huge because
Right.
of the long wavelength of the radio waves. So it seems to me that the development in communication is moving in the opposite direction. So they are moving to higher and higher
Right.
frequencies and shorter and shorter wavelengths, and that kind of
Right.
moves further
S-
away from this kind of
Right.
possibility.
So, like, don't get fancy. Just use a regular radio transmitter and just have a dish on Earth that can receive the signal.
Yeah, I think that kind of seems to be the bottom line. So
Yeah.
I would love to be wrong, but
Yeah.
that's
Yeah.
my conclusion for the moment, at least.
Delicious Plum asks, what might be the average lifespan of an electric solar wind sail? Would one of these satellites last as long as the Voyagers? So how durable are these tethers?
Yes, yeah, that's a great question. So the answer is that we can tune the durability. So by just selecting the number of subwires, so the lifetime increases exponentially as a function of the subwires that the tether is made of. So if we use 4-wire tether, which is our baseline, then the expected lifetime is about of the order of 5 years. But if we use 5 wires, then it becomes much longer. I don't know how much, but it's anyway several tens of years in that case.
Yeah. Is there
So
is there
basically, we
any
can make them durable. Yes.
right. So you can make them more durable. But I mean, we're starting to see some incredible work in 3D printing things in space, especially things like filaments and tethers and things, things where you just, you build them on the spot. So, I mean,
Yeah.
could you build your tethers out of a material that's 3D printed? So if one of your tethers snaps, you just extrude another one from the central bus,
Yeah.
right?
Yes, possibly you could. I mean, we actually looked into this possibility at our lab maybe 3 or 4 years ago, but then we kind of decided that it's too fancy at this
Yeah,
stage of
right, of
development, and then we
course.
went back into making the tethers
Yeah,
on ground. But we actually thought about these kind of things in some phase, and certainly it's not impossible idea, but
right,
it
right.
seems maybe further into
Yeah,
future.
I just imagine like a spider just,
Yes,
a spider
yes.
doesn't, isn't born with however many silks it's going to need, but it just extrudes them as it needs to, and the same thing. You could almost imagine uh, a solar, like you might need different length tethers at different parts of, if a big tether is hard to move, hard to shift your position, hard to change your orientation.
Mm, mm.
Maybe a smaller tether is easier. So is there any value in increasing and decreasing the length of the tethers as part of your mission?
Yes, of course. I mean, if you make the tether shorter, then these tilting maneuvers will become faster. So it's more
Yeah, yeah,
agile mission spacecraft. But then you have to increase the number of tethers if you want to maintain the same thrust force from the
yeah,
sail.
yeah,
So and certainly you are right that if you have some kind of spider system that weaves the whole tether rig,
yeah,
then it might be feasible to increase the number of tethers without sacrificing reliability, because the reliability is kind of the main reason why at the moment we don't want to increase the number of tethers too
of
much. So
course.
we have thought about, or at least I have thought about these kind of possibilities for already for maybe 10 years ago or something like that. But uh, the only reason why we haven't kind of moved forward with these ideas is just that it seems to us that the level of technology that is kind of affordably available right now in space is not quite yet sufficient for that kind of thing.
Yeah, I
But
mean,
certainly things are evolving all the time. So
yeah, it's funny. I mean, from my perspective, right? My job is really to sort of see all of the things that are all happening all at the same
yes,
time, and then to kind of go, oh, this 3D printing over here would be really useful for this electric sail idea over there. But obviously, both of them are in their infancy right now, and so
yeah.
it's way too early to try to sort of take advantage of these kinds of technology. Like, let's see an electric sail actually reel out its tether first,
Yeah.
to start with.
Yes. Yes, Fraser. We are certainly on the same page regarding this. So
Yeah,
yes.
yeah, yeah. No, I totally understand. So another question from Arjun. There are twisting electric fields at the edge of the solar system, as well as like the heliopause. So
Uh,
there's a region in the outer solar system where the solar wind starts to interact with the interstellar wind.
mm,
Will
yes.
will that limit your, is that when you run out of solar wind?
Yes, in theory, yes, but in practice we run out of the solar wind already earlier because the solar wind becomes so tenuous that in most, of course, it depends always on the length of the tethers and the payload. But usually we would turn off the sail already at let's say at 20 AU distance or something like that.
Right,
So
like
so
Neptune.
yes, because I mean we could keep it on, but the speed increase that we get, the acceleration we get after that is kind of so small that
Yeah.
it doesn't really matter. And then, of course, if you keep the tether, if you keep the voltage on after exiting from the heliosphere, then you start actually braking because the interstellar plasma is again much denser than the solar wind, and it's almost kind of
Right.
it's moving much slower. So to first approximation, you can think of it as almost stationary.
Right, right, right. So that would be the situation again where if you built like a really big, like say you just made it ridiculously big tether system, some tens of
Yes.
kilometers, hundreds of kilometers long to get
Yes. Yes.
maximum thrust early
Yes.
on,
Yes.
then you would want to, as you start to get out into that outer solar system, you would want to start snipping away your tethers
Yes,
because
but
you're
you don't have to snip away, because the only thing you have to do is to turn off the voltage of the electron gun. So after you turn off the voltage
right.
of the electron gun, then this magic disappears. So then we have just ordinary wires in ordinary space, and nothing serious
Nothing to
happens.
interact them, right? So you don't need to actually physically get rid of them. And so I guess the same thing. Then you can change the voltage that's going through the. Is there any advantage to using more voltage if you had lots of power? If you had three RTGs bolted into your spacecraft, would you be able to?
Yes, you can press. Yes, so the higher voltage you use, the higher thrust you produce. So it's almost linear relationship between those. But then also the amount of power that you need grows as voltage raised to power 1.5. So it's a trade-off between the available power and the thrust that you want to produce. And also there is some practical limit for the voltage that you can use, because the insulators, the high voltage insulators become thicker when you increase they must be thicker when you increase the voltage. So, and that increases the mass also.
Right. Raj Luthra asks, can electric E-cells collect energy for batteries? So is there any way? No.
This is not an energy collection device.
Right,
So this is a momentum. So you need to use a little bit of energy to keep the sail stretched, so to say,
Yeah.
to keep the tethers under this high voltage. And then when you do that, then you get momentum from the solar wind. But this is not an energy generation device. So this is a momentum generation device, basically.
Yes, but there's no way. Is there a way that you could harness the momentum from the solar wind for electricity?
Not that I know.
No.
Unless you use these tethers as electrodynamic tethers. But then you need some. So if you have magnetic field, but the magnetic field of the solar wind is so weak that you can't really. You in theory you get something, but it's kind of
that's all I needed to hear. That's all I needed to hear was in theory. Yeah.
In theory.
In theory, but so in theory, you could somehow harness from the magnetic field of the solar wind, and then you could turn that into electricity. But it's not very much.
But then it's kind of the electrodynamic tether effect. So then it's kind of different physics than what we are using here.
Yes.
So you could use the same hardware still, but it would be the different physics. But in practice, you can say, the power that you get by that method is so small that it's basically almost nothing. So you can't do that, unfortunately.
Right. But I can kind of imagine, like, you switch the system to gathering energy if you're not needing it for propulsion at all, and then you would switch over to propulsion when you need to go somewhere.
Yes, in the magnetosphere of Jupiter, for example, there this might be done, might be doable. So
right.
So because the Jupiter's magnetic field is so high that kind of changes the situation. But that's a whole other story, and there are many other complications in that application also.
Right. So Aaron is asking, could you add an electric sail on a probe like Orion? Would it add mass? And I think just like in general, do you see a future where, I'll give you an example, like when you have a boat, you have to have another method of propulsion. So if you have a motor on the boat, you also have to have an oar or a sail. Just for safety, as a backup. So,
as a backup,
yeah. And so can you imagine like some sort of standardized electric sail being attached to almost any spacecraft in the future as a backup method. I mean, Kepler, like if Kepler had an electric sail, it would keep, maybe it would be able to keep working. They had to. So when you think about the Kepler, I don't know if you know what happened with the Kepler mission.
Was it so that they had a broken gyro?
That's right. Yeah, Kepler had the broken gyros, and so what they figured out was they were able to balance the spacecraft into the solar wind, where the pressure, or into the sunlight. Sorry, where the pressure.
Sunlight.
Where the pressure of the photons was keeping the telescope perfectly balanced, looking at
us. You mean in the attitude sense? Yes.
Yeah, able to perfectly balance it, and so you can imagine, if you're on an Orion capsule or some spacecraft or whatever, and your propulsion system goes down, or let's say there's not humans involved because the humans are dead, but you've got a satellite that has a propulsion system. It failed to reach its desired orbit, around the moon,
but we have to make a distinction now. So if it's a propulsion system that fails, or if it's the attitude control system.
Let's talk about the propulsion system. So
propulsion system.
Yeah.
Okay, then so you can apply the electric sail to any spacecraft, but with the condition that you have to be outside Earth's magnetosphere, because you have to be in a region where there is solar wind available.
Yeah.
And the other condition is that you must be able to, your mission has to be compatible with slow spinning.
Right.
So and that's kind of one condition. So for example, a space telescope probably cannot spin because they want to point at a certain star for a long time. So
right, and that actually
things like that,
and that leads into. But you can imagine some future where they just you have some module. There's a tether. There's an electric sail just attached to every spacecraft as a backup, and that way it's only a couple of kilograms, and if need be, it could deploy some version of an electric sail and then continue raising its orbit or whatever it needs to do as a backup.
Yes.
Some missions it'll be the primary propulsion system, but you can also imagine in other missions they'll like attach an electric sail because they're small, they're very very few moving parts, and the sun is constantly blowing. So
yes, this is a generic technology, so you can apply. So this is an interesting application. So we haven't been thinking about exactly this application, but yes, whatever requires propulsion, then potentially we can provide.
And in fact, you could almost like have with the plasma brake as well, right? So it's like, every spacecraft should have all of these missions should have a plasma brake just attached to them. Anything that's going to deorbit. All of these constellations,
yes, especially for deorbiting,
right.
This is relevant.
Yeah, they should all have a plasma brake on them.
They should all have a plasma brake because even though these mega constellation spacecraft satellites, they probably have ion engines on board, but because this they can only deorbit this satellite using the ion engine or Hall thruster, Hall effect thruster.
Yeah.
If all the subsystems of the satellite are still working, so they need power. The power system must work. The attitude control system must work, and the thruster must work. Because otherwise, if any of these three fails, then you can't deorbit with
right.
this Hall effect thruster. And that means that there will probably be some fraction of those satellites that are left there as orbital debris because something failed before they deorbit it.
Right.
And so even if the main deorbiting method is the Hall effect thruster, adding this 2 kilogram or adding the small plasma brake, which weighs only 2 kilograms
right.
module, then it would increase the likelihood that they will actually deorbit. And that's actually very important for fighting the orbital debris.
Absolutely.
Given how large numbers of satellites we are talking about in case of these mega constellations.
And then for anything that's going to be operating outside of the Earth's magnetosphere, it makes sense to also attach a auxiliary electric sail just in case you need.
Yes, but of course for a different reason.
Yes.
Because in those orbits, this orbital debris is not a problem.
Yeah. So Young Ziz, sorry, asks, is there a possibility to keep the tether straight without the rotation of the satellite? So that rotation is necessary, right?
At least we think so. We have been trying to come up with some way how to keep it straight without rotation, but I can't. I don't think there is such. At least I don't know such a way at the moment. So
Yeah,
but it's a very relevant question to ask, because this rotation is of course a little bit of a nuisance for many applications. So it would be very cool if we could have a sail which doesn't involve rotation.
Right.
So this is a question that we have been thinking of a lot, but at the moment we can't really.
Right.
We don't have a solution.
And so that rotation of the spacecraft is what actually deploys the tethers themselves and keeps them taut, keeps them stiff in all directions.
It's a centrifugal force which keeps them taut, keeps them stretched.
Yeah.
Another way out of this problem would be that if you have some kind of magnetic linkage between the rotating part of the sail and then non-rotating spacecraft, which is somehow sitting at the middle of the ring or something like that without any physical contact with the rotating ring. We have been thinking of that kind of stuff, some kind of magnetic confinement of the spacecraft, but it's hard to do without superconductors. And then if you go into superconductors, then you introduce the reliability issue because you need this active cooling. So, but if somebody comes up with room temperature superconducting, then we are talking. Yeah. Then we can
finally.
We can use that's yet another application for room temperature superconductors. How to connect spacecraft together in space without actually connecting them physically.
Right. Yeah, but if room temperature superconduction is developed, then everything changes.
Yes, many things change. Yes, but including also
orientation of spacecraft missions. Yeah, that's great.
Yes.
So this is interesting. So Dagrith asks, could a magnetic brake be used to decelerate a spacecraft to enter orbit after, since all of the outer planets have their own magnetic field? So, I mean, for example, right now, Mars, a spacecraft that's going to Mars might use aerodynamic braking to enter Martian orbit.
Yeah.
Could you do something similar with the plasma brake, or is it just too slow?
I'm afraid it's too slow because I mean we have to make a distinction between aero braking and aero capture.
Yeah.
So aero capture means that you really create a rather large delta V at one rather large velocity change during single pass through the near the planet. So what limits us in case of Jupiter, for example, is that even though Jupiter's magnetic field is very large, so we could. From that point of view, we might generate a lot of force in the near flyby, but the problem is the mechanical tensile strength of the tethers, because that kind of limits the maximum force that we can transmit to the spacecraft, because the force is transmitted by these tethers.
Yeah.
So I would say that this capture by this effect is probably out of question.
Yeah.
But braking is certainly feasible. So we might do capture by a small chemical thruster, for example, in case of Jupiter, because in case of Jupiter, you have very massive planet, and then this Oberth effect magnifies this even a small chemical burn to a high extent. So you might do the capture to highly elliptic orbit with chemical means, and then you can start to slowly decrease in the aphelion of this elliptic orbit.
Right.
By using the low thrust propulsion.
Right.
That's right, this one, yes.
Yeah, I mean, one of the advantages of being able to fly to Mars is you can do this very fast trajectory and then do an aero capture to be able to arrive without having to carry a lot of propellant on board. And so any idea that will work. We've reached the end of our time. It's been absolutely wonderful and really enlightening to understand every aspect of this technology. I think as people understand, I'm really excited about it, and have covered it a lot in the past, and will continue to cover it in the future. Where can people find out more about what you're working on and what's happening next? What is the next big development that people should be watching out for?
I mean, the next thing is that we will launch these two CubeSats hopefully next year. So this For Sale 1 and S-Cube 2, or at least one of them, hopefully will be launched already during next year, and then this North Star mission.
Yep.
But that doesn't have kind of launch or stable funding yet.
Right,
but it's
right.
But there is a company with more than 20 people working there who are kind of propagating it. So those three things.
And if people want to follow the developments, where should they go? Where should they?
To our website. So that's www.electric-sailing.fi.
Okay.
Finland.
And I'll put a link. I'll put a link into the show notes so people can find out more. Well,
yes.
Dr. Janhunen, it was an absolute pleasure to talk to you. There's a lot of fans out there cheering and rooting for your work. And please let me know when you guys do something. You've got my email. Let me know when you have something.
I certainly do.
When you have something new that's happened, and we can't wait to get the word out.
Yeah, thanks, Fraser. I very much enjoyed talking to you. It was really big pleasure for me. You are so. You have so wide knowledge, and you are so expert in everything related to space.
I hope you're taking notes. Maybe if you have any if any of the ideas pan out, please let me know.
You gave me lots of new ideas already during this 1 hour.
Perfect, wonderful. Then that's my job. All right.
Yes.
Thank you. Take care, and I hope you all stay safe.
Yeah, stay home and stay safe. And
excellent. Thank you.
Bye.
All right, I'll stop.